Welcome everyone. Welcome to our computer science colloquium. And today's speaker is Kevin Bock from the University of Maryland. And he's currently a PhD candidate. And then his research area in network security and also internet censorship. Okay. So today we actually can expect that, that what's going on with the internet freedoms. And he also has been an adjunct faculty for the University of Maryland, and where he created upper level undergrad, security course, basically, hands-on course, and some kind of network penetration testing, etc. Okay, so to make sure that we have a talk, we listen carefully. So for the participant joining from Zoom, you guys actually can leave your question in the chat, and then who have to join in person, feel free to ask questions. Okay, so for more interactive discussion. Okay, welcome, Kevin. Yeah.
All righty, thank you, everybody. So thank you so much for the intro. My name is Kevin Bock from the University of Maryland, and I study how to make the internet a safer and more secure place, really, so anyone can communicate with anyone they need to. But this internet freedom, this ability to communicate on the internet, is under threat by powerful adversaries every day. And this really takes many forms across the internet. But this is everything from Cambodia's new censorship and surveillance system. Oh, am I blocking? I'm so sorry. Let me slide out of your way here. Is this any better? A little bit. Yeah, better. Good. All right. Should have tested from different seats while I set this up. Sorry about that. Okay. So just a few examples. New censorship systems rolling out around the world, or even cyber attacks on the Ukrainian government in the lead up to Russia's invasion. So this is happening more so all the time. And really, these attacks have fallen into two broad categories. And this internet freedom is under threat from two of the broad things attacking this internet freedom are that of nation state censorship and denial of service attacks. Okay, the censorship infrastructure, these operate at nationwide scales, controlling what citizens can and cannot access inside the country. There's also large scale denial of service attacks that bring down important infrastructure, election monitoring systems, and posting political views. But both these attacks, although they work differently under the hood, they share a common goal, right, of stifling open communication on the internet. And a commonality that these things share in many cases is that they are powered by, or can be powered by in some cases, something that was never designed to be part of the internet in the first place. And that's this idea of Middleboxes. Now, when two end hosts communicate online, okay, client and server, when they communicate, we often think of the network that connects them. It's just a dumb system that routes packets around. Okay, and this is what it was originally designed to be, actually. This dumb middle of the internet was a core design tenet of the original internet called the end-to-end principle. But that's not really how it works anymore. Because nowadays there's smart computing networks in the middle of the network all over the place. And these take many forms: firewalls, intrusion protection systems, intrusion defense systems. We call these Middleboxes, by the way, as I said, it's the middle of the network. That's Middlebox. So when these hosts for a variety of applications, monitor network traffic, maybe they intercept network traffic or monitor what's going on, but they're manipulating traffic. And overall, these Middleboxes are at the heart of this fight for internet freedom. In many cases, Middleboxes are powering some of these attacks. The nation-state censorship around the world is powered by many of these Middleboxes. A lot of this nation-state censorship infrastructure is effectively run by nationwide firewalls, which is these Middleboxes. And denial of service attacks, we've seen this happen in a couple cases where firewalls can launch these attacks through block page injection. Studying these systems, though, is really difficult, in part because they were never designed to be a part of the internet in the first place. And even broader than this, these systems have a couple properties that make them harder to study than some things we're used to. These systems are closed. Right? I can't just download the source code from the Great Firewall of China. They're opaque. They don't tell you how they work. There's no open standards that govern how these things operate, how they work. So they've been challenging to study and challenging to understand from the outside. My approach and my agenda in this space is to study these systems and develop, more specifically, automated techniques that help us study and evade these increasingly complicated network threats. My approach breaks down into two broad categories. So first is automated discovery of systems. developing automated techniques that allow us to study and understand how these systems operate, and then perhaps elicit some unintended behavior, right? Bug hunt these things. And then after the fact, combine this with internet-wide measurements to understand what's the impact of the things we've discovered, okay? Oftentimes internet-wide. And then just some additional aspects of how I work as a researcher. I often engage with activists and industry to deploy solutions. Where it is ethically and appropriate to do so, I open source and deploy findings. So most of the code for the projects I'll talk about today is open source and available. If anyone would like to check it out while I'm talking, you're welcome to. And lastly, I'm passionate about scaling up undergraduate research. I mentioned this very briefly at the end of my talk, but if anyone wants to talk more about it after this talk, I can. So I've been applying this approach in two broad domains throughout my PhD. And I'm going to talk about this in today's talk. So the first thing I'm going to speak to is new ways of automating censorship evasion research. And then I'm going to pivot to discovering how my work on discovering new network attacks, and specifically how we discover that Middleboxes and some of the systems can be weaponized to launch attacks against innocent people. And then I'll conclude with some future work. But the first thing I want to speak to is this idea of automating censorship evasion and how we can discover new forms of evading censorship, even in complicated systems. This work first appeared in CCS in 2019. Before I get into the details, I want to give everyone just a quick background on what nation-state censorship actually looks like on the wire today. Okay? Because there are many nation states that operate censorship like this. And just to clarify here, there are many types of censorship that operate around the world: political pressure, misinformation, disinformation, you can go on and on. One of the most pervasive forms of censorship out there is this automated in-network censorship that's operated by nation states. These things run 24 hours a day, 7 days a week, and they monitor basically all internet traffic that crosses these countries' borders. And that's the internet censorship that I'm talking about today. The mental model many people have when they think about censorship looks a little something like this, where the censor is physically sitting in the network path. And this is how some countries implement censorship. Many other countries, actually, it's difficult to get machines on all the internet paths. So instead, they sit on the side of the path. They're not a man in the middle attacker, they're a man on the side attacker. And there are some implications into how censorship is done when you have attackers set up like this. Let me show you an example. Let's say we have a user in China, and they're going to try and reach some forbidden resource in China. Wikipedia is actually censored today in China. This user will make a request, and this request will move to the network. And you'll notice that even though this request is forbidden by the government, Wikipedia will still get it, and the censor will just get a copy of it. And what the censor does here is it applies deep packet inspection. It looks at the contents of the packet, parses it apart, discovers that this is going to some destination that's disallowed. And then what it does in order to censor this connection, it can't drop the traffic. It's off to the side, and the server's already got it. What it does instead is it injects its own packets into the connection. And specifically what it's going to do is it's going to inject spoofed teardown packets or reset packets. These are normal packets, our computers send these all the time. And they just exist to tell the other side of the connection, stop talking to me. Okay? And it's going to send two of these. It's going to send one to the client, pretending to be the server, and one to the server, pretending to be the client. Both sides of the connection will receive these packets from the censor. They'll think the other side sent it. Both sides will stop talking to each other, and just like that, censorship has been achieved, right? But in order to pull off this attack of injecting teardown packets, you'll notice that the censor needs some information about this connection. It needs to know the port numbers. It needs to know the sequence of acknowledgement numbers. In effect, it needs to be tracking per connection state. Okay? These Middleboxes are state-constrained entities. They can't just store things forever. Okay? So if you're trying to operate this attack at scale of the nation, this means you need to literally be tracking the state of every single TCP connection into and out of the country at all times. And to pull this off, you're going to necessarily have to take some shortcuts along the way. Some of these accidental, some of these by definition. And we as evaders can take advantage of some of these shortcuts. Let me show you an example from prior work, where researchers in the past discovered how we can take advantage of some of these limitations to defeat this type of censorship. So once again, we're going to have our client, and they're going to try and make this connection. But before we do that, we're going to inject a packet into the connection of our own. We're going to inject our own reset packet. We're going to send it such that the TTL, the time to live of this packet, we set it in a special way. The TTL is a field that exists in all packets, and it controls how long the packet lives in the network. It decrements once per hop, and once the TTL hits 0, the packet is dropped. So we're going to set the TTL high enough that this packet will reach the censor, but not so high that it will reach the server. When we send this packet through the network, you'll notice just like before, the censor gets a copy of the packet, right? But it's not going to make it to the server this time. It gets dropped along the way. Now the censor sees this packet and it thinks the client just shut down the connection. And if that's the case, the censor doesn't need to keep track of the state of this connection anymore, right? It throws away the state it's tracking of this connection. And now for the rest of this flow, the rest of this communication, the client and server are free to communicate censorship free. The server has no idea we pulled off this trick, and the censor, even if it wanted to censor us, it has no state in which to do so. Okay. This is just one example of an attack that researchers in the past have developed. And this attack takes advantage of a fundamental limitation of Middleboxes called the eavesdropper's dilemma. And the eavesdropper's dilemma states that if you're in the middle of a network and you're eavesdropping, it is difficult, not impossible, to know for certain what the state of the connection is at the end. Right? The censor does not know. The machines on each side, the connection is still valid, or the connection has actually been, he thinks the connection has been torn down, the connection is actually still valid. But this is just one example of these attacks that have been developed over years. But many of them don't work anymore. Okay? And there's some challenges in developing these systems, these types of evasion strategies. One of which is that censorship is an incredibly diverse ecosystem. Okay? Different countries censor different things in different places over different protocols in different ways. And all of this is opaque, right? And none of this is announced to us. And what's worse is that all of these systems are constantly adapting and changing to what we as researchers are doing. And really, this comes down to how we've been approaching this research in the past. And this diagram, well, the title slide, I know you guys couldn't see this. Should I move this?
Yeah. Can you move a little closer to the speaker?
Oh, certainly. Well, I'll block you just a tiny bit, or I'll just shout. So it comes down to how we've been doing this research a lot in the past, where we start by hypothesizing and taking measurements, which I'm trying to move this thing out of the way, and really understand how sensors operate. It's basically a scientific method, right? And then afterwards, we apply our good human intuition, apply our insight into creating some evasion strategies. But the problem with this method to this space of censorship is that we've been doing this manually. And we're at this asymmetric disadvantage to censors. Like I said, these things are black boxes to us. We have no idea how they operate. And they don't tell us how they operate. So we can put out some solution, and we have to work hard to get to that solution. But they know their code. They can update their code very easily, and sets us right back to square zero. That's why this manual effort has been giving censors the advantage in this arms race for the last several decades. So my work in this space has been trying to flip this around and give evaders the advantage. So the model I'm proposing today looks a little something like this: automated censorship evasion research. Okay. And in this world, we create an algorithm that automatically discovers a way to evade censorship. Okay, we evade from step one. And then we can put those things out there for those who need to get past the censor and help them evade very quickly. And then after the fact, we as researchers can go back and look at the results of this algorithm to understand how the censor works under the hood. It's almost like how it's easier to show your work when you already know the results of the math problem, right? You work backwards in that way. So I've built and designed the system. We call it Geneva, which stands for genetic evasion. It's a genetic algorithm. For the next few minutes, I'd love to show you the architecture of how I built Geneva and then some of its results from running around the world. So Geneva is a genetic algorithm, which is a learning system. It's a biologically inspired learning system. And if you want to build a genetic algorithm, there's a couple of things that you need to do. You need some building blocks. You need some way to put those things together. You need some way for those individuals to mutate and mate between generations. And then lastly, you need some sort of fitness function, something that identifies which individuals are fittest and should continue to survive and propagate their genetic material forward. Now, looking at this, it's very not obvious how to apply this idea to the idea of network security in general, nevertheless, censorship evasion. So let's walk through this piece by piece, and we'll build up to the idea of Geneva. We're going to have Geneva running strictly at one side of the connection, and it will be manipulating packets as they enter and leave. And right now, this immediately hits us to our very first snag in this design, because if you think about it, there's a whole lot of ways to give an algorithm the ability to manipulate a packet, right? On one extreme, we could give it the ability just to manipulate bits. It sees some bits and it can flip them, right? This is a very versatile idea, but unfortunately could also be very inefficient, right? You can imagine it struggling for years to grapple with the idea of a checksum. On the other end of the extreme, we could build the algorithm and encode it with the known strategies, some of human knowledge in this space of packet manipulation strategies. This could be very efficient, but also limiting. We'd be encoding past human biases into the system, limiting what it can discover. So instead, what we did, we stepped back and asked, what is our goal with these packet manipulations? What we really want to be able to do is give the algorithm the ability to transform any sequence of packets into any other sequence of packets. And to do those operations, really, if you think about it, the only things you need to be able to do are the same things that the internet itself can do, what IP and TCP can do. So specifically, we give it 4 actions that it's allowed to work with. Okay? It can duplicate, so it can take a packet, make 2 packets. It can tamper, which means it can take a header field of a packet and change it in some way. We can fragment a packet, which is take a packet, break it in 2 pieces, and then drop a packet, which is exactly what it sounds like. You just take the packet, drop it on the floor. And I'll call out 2 things specifically here. For tamper, we allow it to alter or corrupt any TCP/IP header fields. But importantly, we don't give it any semantic understanding as to what these fields mean. What I mean by this is that the algorithm can see the TCP flags field as a field it can change, but it doesn't know that changing it to SYN means the start of a connection. So we give it syntax, but no semantics. I'll call out one more thing specifically here. The fragment action technically does double duty. For the networking folks in the room, at the IP layer, it does fragmentation, but it can also do segmentation. So now we have a set of building blocks. Now we need a way to compose these things together. And this action system actually lends itself nicely to this, because we can compose these together in trees. And specifically, we build these as action trees, or trees of actions, where you can, the results of one action can chain directly into another action. And we add one more component to these action trees, which is this bit at the top, this trigger. And these effectively operate as match action pairs. Okay, so this trigger at the top defines which packet should be modified. So this says an outbound TCP packet where the flags field is at, we should modify this. And the action tree itself describes how we should modify it. Okay? Now, I won't make you run through this in your head. Instead, let's see an example of this strategy running on the wire. So once again, we have our tracker client about to make a connection. And this client is about to finish setting up this connection, which means it's going to send an ACK packet. And Geneva will see that this packet matches an ACK trigger, so it pulls it into the tree. We duplicate it. The left child we're done with. The right child, we change the flags field to reset, TTL to 2, and then we send the packets that emerge. And if you'll notice what this tree just did, is this exactly implemented the strategy that I was talking about, right? We just injected a TTL limited reset to this connection. And in fact, we were able to go back to this entire space of prior work, and to prove to ourselves that this was expressive enough, we were able to implement prior work strategies in this strategy space. This gives us great confidence that this is expressive enough to implement the things we need to do. Next, we need to talk about mutations and mating. And this is actually one of the easier ones, because you can just use your imagination, and there's all sorts of ways that you could mutate these trees, match them together, pull them apart, change a protocol to another. I'll refer you to our paper for the full list. Lastly, we need to talk about the fitness function. Because when Geneva's training, what it's effectively doing is it's trying out each of these strategies, and it's trying to obtain some forbidden content through a live sensor. And these strategies are manipulating that network traffic for each connection. And the goal is basically for Geneva to try and identify which strategies perform the best and which should continue to live on. Now, of course, the problem is that not all strategies are going to work when we start, right? When it starts, it's actually going to be very bad. So how do we build a fitness function in such a way that we can guide the algorithm, even though the sensor doesn't give us any gradient with which to learn? Whether sensor or not, there's no machine learning gradient for us to work with here. So what we do when we build this fitness function is it comes down to what behavior of the algorithm do we want to reward, okay? And so this fitness function is a tiered system of punishments and rewards. The first thing we do is we punish it for not triggering on any packets. And what this does is it encourages the algorithm to come up with strategies that trigger on active connections. So it's actually applying its work and doing things that matter. Next, we punish it for breaking the underlying TCP connection. And what this does is it encourages the algorithm to search only the space of strategies that keeps the connection alive, which we want, right? We can't have the algorithm shooting itself in the foot. Next, we reward it for successfully obtaining forbidden content. We beat censorship, great job. And we could stop right here. This could be where we stop. But we optionally add one more reward for conciseness. And the reason this is that we're rewarding the algorithm for simplifying the strategies down. I have a small human brain, and it is easier to understand a 2-action strategy compared to a 50-action strategy. This comes down to explainability of the algorithm, rewarding it for explainability.
So you're rewarding sparse.
Kind of, yep. And that reward only happens if there is a success. So it comes at the end, yeah. So this is Geneva in a nutshell. Now let's talk about how we can evaluate these things. And this is one of the great challenges of this work. Because in order to evaluate this type of work, really what you need to do is be issuing these forbidden requests through live censors. And in many cases, this involves having vantage points in these countries. And in many cases, procuring those vantage points can be quite difficult. I mean, the US government has trade sanctions against some of them actively. Other places, it is flatly illegal for me to buy these machines. So performing this training is actually quite difficult. And over the years, I've been working with the Asian community, and I'm fortunate that I've been able to develop these relationships with researchers, activists around the world who've helped us to run these experiments. So overall, I'm going to talk to real censor experiments we've run in all of these places against all of these protocols. And in total, across all of these cases, Geneva has been very successful. But I want to give you an example of two strategies that it's found in the client side in this batch of results. Okay. The first strategy I want to talk to should look very familiar to you. This is the same strategy I opened this talk with. Geneva re-derived it, and it still works today in China. Okay. It still works, yes. If anyone's curious as to why this still works, I can talk at much greater depth at the end as to why we think this has been so hard for me to fix. Okay. But next, I want to show you something novel, and something that Geneva discovered that's new. This is a slightly more complicated strategy, so I'll run through what this is. This is a segmentation strategy. It takes the user's request and it effectively breaks it up into three pieces. So if we have a request that looks like this is a search for a keyword ultraserve. Ultraserve is the name of a circumvention tool that the Chinese government is trying to restrict knowledge of. So this keyword is censored. When we first saw this strategy, we thought this was very surprising because famously, for the last decade now, the Great Firewall has had the ability to reassemble packets. So if you took your packets and break it up and sent it to the censor, the Great Firewall would just see what you're doing, put it back together, and then censor you. So for the last decade, researchers had thought that this type of strategy was not possible. They directly said this, actually. We didn't tell Geneva this was impossible, so they explored the space anyway, and actually discovered a way through it. Now, when we first look at this, we're like, okay, maybe what's going on is it's just taking the forbidden keyword and it's splitting it up into lots of pieces, and that must be what's going on. But when we actually run this strategy, what we find is that the forbidden keyword is all in plain text, unharmed, in one single self-contained packet. Okay? So as to why this works, we still don't know for sure today. We believe this is a bug in the Great Firewall of China, and specifically in how it identifies the HTTP protocol. But the reason I share these two strategies is because I think they're more broadly emblematic of the types of strategies that you need to find. On one hand, we have these more systemic, fundamental issues, right? This is the direct consequence of the eavesdropper's dilemma. And this is a fundamental design flaw that's difficult for them to patch. On the other hand, we have these, likely as a software bug, right? Maybe it's not by one, maybe they're not handling packets correctly, right? But software bugs and these more systemic design flaws. Really, what's important is that Geneva can discover both of these types of things. And overall, we found these two strategies, but these are actually just two of many. And in total, we found over 80 strategies in total in this space. And it was able to actually rederive all of prior work in this space, more or less inaccurately. Just gives us really good confidence this could be useful. Yes?
So you listed the protocols here, HTTP,
Yep.
Other protocols, but
Yeah.
there are also protocols which encrypt the data. Right? So when you do the segmentation of the GET request,
Yeah.
how would you deal with the packet data as completely?
Yeah, so it's a really fun question. The answer comes down to two things. So first, that strategy I just showed only works for HTTP. And actually, one of the results of this work was demonstrating to the world that censors censor different protocols and different mechanisms. So like strategies that work for one protocol won't necessarily work for another. That being said, your question of, I think you're asking a broader question of how do censors censor these encrypted comms, right? The answer most of the time is that they don't deal with the encrypted piece. So HTTPS, for example, is an encrypted protocol. But HTTPS has a field called the SNI field, server name indication. This is a field that's in plain text, the very first packet you send. The client has to announce what domain it's talking to. Every censor around the world that censors HTTPS, by and large, they just read that field and kill your connection. So there are encrypted communications. Most censors are not dealing with encryption. They're just reading what's in plain text and taking it down. There have been some more recent advances in censors working over encrypted communication. 2 months ago, the Great Firewall of China rolled out a new system targeting shadow socks. And I can talk, we haven't published anything about that intentionally. I can talk more offline if you want to hear more about how some of these systems work. But censors are developing capabilities toward these encrypted systems, but most of their vanilla protocols are not that sophisticated. Say again?
Can you repeat the question?
Oh, certainly. So the question, just for anyone in the Zoom audience who didn't hear, was how are censors censoring these protocols that should be encrypted? Yes.
I'm just wondering, your system is open source, right?
Correct.
So why can't China use it and strengthen their file sensor?
So I'm going to ask you to hold that question for 2 minutes because I'm going to come right back to that.
Yeah.
Yes.
So in the rank order of the number of new exploits that you found,
Yep.
it mirrors somewhat the number of protocols. Is it because of the diversity of the protocol? Like, is the China one doing a lot of DNS things, a lot of SMTP in addition to HTTP? Or is it predominantly able to find new evasion mechanisms in just one protocol?
Yeah, so insightful question. This is partly the result of many protocols. It's partly the result of censorship complexity, like the complexity and sophistication. Ironically, the more sophisticated systems are often the ones where we find more strategies, just because the attack surface is so much broader. So it's a combination of sophistication, more protocols, more opportunities for takeout, things like that. Yeah. Okay.
Is this also a way to characterize the complexity of the system in the sense that, like, I think when you're showing India had not in the number of strategies, I think in the number of strategies in this one. In this case, are you saying that the censorship wall of India has only blockade for HTTP, but the other protocols are not blocked? Is that the theory?
So in many cases, yes. This slide is actually, I realize there's a missing piece for HTTPS for India. India, as of 2 years ago, is now also censoring HTTPS. I must have missed that. I wouldn't classify number of protocols as in sophistication, because there can be very sophisticated protocols, that sophisticated sensors that just target some protocols. So I wouldn't want to say less protocols means less sophistication. I mean, censoring SMTP, for example, is a very straightforward thing. Just China's the only one that's put in the effort to do it. Yeah. So I'm going to keep talking about a little bit more in the censorship space. There will be more opportunity for censorship questions. But so moving on from here, this is how we've used Geneva to automate the discovery of new evasion strategies. And from here, I want to shift gears a little bit to an exciting direction we've been able to take this work from here. And this is the idea of server-side evasion. And this work first appeared in SIGCOMM in 2020. I was also fortunate to win IRTF's Applied Network Research Prize. So the idea of this is that censorship evasion research is always involved the client. And the sentence sounds so obvious to say out loud that it feels almost silly or axiomatic to say it, right? If the client wants to evade censorship, the client should have to do something. But this sentence or this idea has always been the biggest blocker for deployment for a lot of these systems, right? Deploying the software can often pose risks to users. Many users don't have the technical know-how how to set these things up. And there's a whole class of people who don't know they're being censored in the first place. Now, ideally, servers could help, right? Instead of deploying software at the client, what we would do instead is deploy the software at the server. And then the idea is we'd have the server subvert censorship on the client's behalf, okay? And we just think about the benefits of this, right? We would immediately broaden accessibility, reachability, clients get plausible deniability, right? This would be very impactful. The problem is when we first approach this problem, and this is the flaw of many great ideas, is that it shouldn't work. This is a bit of a bummer. And the reason why it shouldn't work, well, let's consider the waterfall diagram of packets that are exchanged leading up to the client sending a censor keyword. Okay, for those who've not seen a diagram like this before, a waterfall diagram describes the sequence of packets that are sent back and forth. So time moves downward. So the client starts by sending a SYN, the server responds with the SYNAC, the client responds with MAC before the client sends the connection, their request. You'll notice here in this diagram that the only thing the server is doing here is sending the single SYNAC packet. And the server can't influence the state of the connection at all after it sends this packet before it matters. And since the client's the one starting the connection, well, the server can't influence the state of the connection before it receives the SYNAC. So the window of time for a server to do anything at all is really, really small. So to study this, I led a team of undergraduates to port Geneva from the client side to work at the server side. And we trained Geneva around the world against these censors. And amazingly, it discovered ways to defeat censorship. I want to show you an example of a waterfall diagram of a strategy that works in China. Okay, this looks pretty ridiculous. So I'm going to walk through what the strategy is doing. The client starts with a SYN packet. But the server does not respond with a SYN-ACK. The server responds with a SYN packet of its own. And this is legal. This is called a TCP simultaneous open. This is an archaic feature of TCP that's still supported by basically every major platform. This is the equivalent of someone coming to you and saying, knock, knock, and sorry, knock, knock joke, and you just respond with knock, knock, and now it's your knock, knock joke. Okay? After we send this SYN packet, we send a second SYN packet, and this SYN packet contains a payload. And this is also legal. This is how SYN cookies are implemented. Now, when the client receives our first SYN packet, the client sends a SYN-ACK. This is just a normal TCP simultaneous open works. But it's actually this combination of a SYN-ACK coming from the client, immediately preceded by a SYN packet with a payload, that causes the Great Firewall of China to desynchronize from this connection. We actually believe this is an off by one bug in how they process handshakes. And this seems ridiculous, but this actually works with varying degrees of success across all the protocols we studied in China. For context, if you do nothing at all, your success rate is going to hover around 2%. And this is one successful strategy, but it's actually one of many. In our original paper, we detailed 11 different attacks across all of these countries, and we've discovered more since then. But across the board, across all of these strategies, what I want to emphasize is that none of these require any client-side deployment at all. Okay? It may induce some behavior from the client, but that behavior is the default behavior of that TCP stack. The client doesn't need to configure or do anything. Now, to step back, though, and just talk about Geneva more broadly, as we've been deploying in these different countries in different circumstances. Censors have been continuing to adapt and evolve as we've been doing this project. And censors have been continuing to roll out new systems. And fortunately, we've been able to use Geneva to do rapid response to these censorship events. These are 3 examples of censorship, new censorship systems that were rolled out quietly. We were able to use Geneva to evade these systems across the board, usually within an hour or 2. This is really impactful where you can respond very quickly. But in general, the work doesn't stop once we've found these strategies, because we can often use these strategies to reverse engineer how these sensors work and how they open them up a little bit and understand how they work under the hood. And even beyond this reverse engineering process, my team and I have been working with a number of anti-censorship groups around the world to get some real world deployment of these strategies. So 2 organizations that I can speak to today are Siphon and TunnelBear. Siphon is an anti-censorship tool, TunnelBear is a VPN. Both of these organizations are currently working to deploy this server-side strategy like this. Now I'm going to come back to your question. It's a great question. Doesn't this help the censor? Right? Like you just stood up here talking to us all about this new fuzzy you made. You're finding all these bugs. Like, why can't China just download your tool and use it? And the answer is that they can. Right? I'm not standing up here saying that this is going to end the arms race. It's not at all what this is doing. This is fast forwarding the arms race. And it's doing it for both sides. So this really raises the question of what's the logical conclusion of this arms race? Where is this going? And I think what this comes down to is these 2 different classes of strategies that I mentioned earlier. Because in reality, these bugs are likely the low-hanging fruit, right? They're probably easier for censors to patch. Maybe they need to work with a third-party vendor. Maybe it's an effort to roll these things out. But at the end of the day, if it's a software patch, they can probably do that more easily. But if it's a more systemic limitation, some fundamental gap in design, or a direct consequence of the eavesdropper's dilemma, or the Middlebox deployment, those are likely a lot harder to fix. So the logical conclusion, hard to say. Likely the case the bugs won't last as long, but these will be much more long-lasting. Okay? And then to take another step back, in theory, censors have had their code for the last 2 decades, and they could have been fuzzing it this entire time. By releasing the system, we're effectively democratizing the ability to fuzz these systems. So it's more than just what the censor can do. Okay, so this is Geneva applied to censorship. Yes, please.
Use these Middleboxes like the sensors. Do they look at the both directional traffic or just one direction?
So it's kind of a complicated question to answer. The answer is they usually look in both directions. As far as censorship goes, it depends on who initiates the connection. So we classify systems as bidirectional if it doesn't matter which side the client is at. Most of the time, once the client query is through, it does not look at the server's response. Does that make sense? So bidirectional, that it doesn't matter which side the client's on, but once the client is started, they're only considered that direction most of the time. Yeah. Okay. Here, no other questions for now, so I'm going to tentatively move on. There will be more time at the end for questions. So, lastly, what I want to talk about is discovering new network attacks. And specifically, I'm going to talk about how middle boxes can be weaponized. I have to give a special shout out to this paper. This was actually a collaboration with folks here at Colorado. Abdul in the audience and Eric in the audience are both co-authors of this. And all this work is thanks to some of the Colorado network team. So this institution deserves a lot of the credit of this work. This work appeared in Usenix in 2020. I was fortunate to get a distinguished paper award from Usenix and win third prize in Facebook's Internet Defense Prize. Let's talk about this paper. Now, the goal of this attack and denial of service attacks in general is for some attacker to flood and overwhelm the bandwidth of some victim, and generally make them unavailable. Now, a powerful tool in the arsenal of such an attacker is the idea of a reflected amplification attack. And the way this works is the attacker relies on some open server to assist them in launching this attack. What the attacker is going to do is it will pretend to be the victim by spoofing its source IP address. It makes a request to the open server. And when the server sees this, it thinks the victim made the request. The server dutifully responds, ideally with something much larger. The attacker, sorry. And we can quantify the amplification factor. How much bigger was the attacker able to make their traffic by the difference between the response and the request? Okay. And historically, there have been some very large attacks in this space. DNS, NTP, Memcache feeds, A3 response. Okay. But one thing that most of these prior attacks have in common is that they've all relied on UDP. And the reason for this is that UDP is a connectionless protocol, which means there's no setup needed for the client server to start communicating. So it's very amenable to this idea of just pretending to be your victim, sending a request, and letting some large response go through. But historically, TCP has largely been spared from these attacks. And the reason is that TCP requires a three-way handshake at the start. So if you try and send your SYN packet to the open server, and you try and spoof your source IP address for this, the open server is going to send the SYN ACK to the victim. Okay? And as a consequence, the attacker is going to be missing the crucial bits of information that are included in the SYN ACK. You can't finish the three-way handshake. Even if you try and fake it, you're not going to be able to do it correctly. Okay, and the server is going to shut this down. So historically, there's been some small amount of amplification in this piece of the TCP stack. But the real meat of this exchange, this request and response here, has largely been believed to be off limits to attackers. And this, basically in TCP, there's been no attacks in the space of reflected amplification until this paper. And what we showed here is that TCP-based reflected amplification is both possible and it can be effective. And I'm going to walk through 5 different attacks we discovered across millions of amplifiers and showed how there could be startlingly large amplification factors. And in some cases, actually, we discovered technically infinite amplification. And the key insight behind this work is we can use middle boxes themselves as the amplifiers. Let's see what this looks like. Nowadays, if an attacker is sending packets to the internet, to our open server, right, the network has grown more complicated since we last reasoned about this. And oftentimes, there can be a middle box in the path. Right? We talked about this earlier, right? There could be firewalls, intrusion detection systems, or in many cases, nation-state censorship infrastructure. But these systems have a few properties that actually make them very attractive targets for these attacks. First thing, these middle boxes expect to miss some packets, right? They have to be tolerant to this. Maybe there's asymmetric routes. Maybe the routes change. Maybe there's multiple middle boxes deployed in parallel, and there's load balancing between them. Okay. So, for example, if a middle box just sees an HTTP GET request for some resource, and it didn't see a three-way handshake, most of the time the middle box just has to assume the handshake already happened. And this isn't even a bad assumption most of the time. Like, why else would this request ever exist, right? If there wasn't a three-way handshake. Okay. The second thing that makes them an attractive target for this attack is that middle boxes commonly inject traffic when they want to block connection. Okay, maybe this is a fake response. Maybe this is a reset packet. Or in many cases, this could be a block page. Okay, and some of these block pages can actually be kind of large. So what the middle box does to inject this traffic is it pretends to be the destination. It spoofs the destination and then sends this block page to the victim. So in general, these middle boxes, in effect, make TCP-based amplification possible because they allow us, broadly speaking, to skip the three-way handshake, and they'll reflect something to the victim. Now, I'm being a little hand-wavy here, but this leads us with 2 big questions. Which packets best trigger these middle boxes? Because the hand-waviness I'm referring to is that it's not always enough just to send the request. Sometimes you have to be a little more clever than that. And the second thing is, and the harder question to answer, is what amplification factors are actually attainable on the internet at large? How bad is this attack? So the first thing we want to answer is what packets best trigger these Middleboxes? And answering this question, we're studying weaknesses in a TCP implementation, not the TCP protocol itself. So we cannot just download the TCP RFC and read it and think really hard. We need to actually study a wide variety of implementations in the wild. And because we need to discover effectively bugs in these systems, ideally we'd have an automated way to do this. So to do this, we actually used Geneva. And what we did was we took the fitness function and replaced it with a different fitness function, where we just rewarded the algorithm for obtaining the maximum amount of amplification it possibly could. And we ran Geneva across a wide variety of sensory Middleboxes around the world. We trained it almost 200 times in these Middleboxes around the world. And then overall, we could do the result of Geneva is a sequence of packet sequences that when we send these, elicit a large amplification factor from these Middleboxes. Okay. So what did Geneva find? In general, we found some broad ways that we can elicit amplification. The easiest is exactly the example I gave before. Just send the request, right? Just skip the three handshake completely. But also found some sneakier ways you can do this. It found that for some Middleboxes, you could send a SYN packet before you sent the request, and then just send the request. Just like pretend you started with a three handshake and then send the request. And for most Middleboxes, that was enough. We also found another sneaky class of these packet sequences where you took a SYN packet and then you stuck the request on the SYN packet itself. And that's something that should just never be valid. For many Middleboxes, it tricked them into thinking it had both seen a through a handshake and seen a middle request. And we found that these requests could be on either push packets or push out packets. So in total, we find 5 packet sequences that we can use for these attacks. And across the board of these, Middleboxes can be triggered without sending any acts at all. Right? No through a handshake would need to complete it. You notice this only solves half the problem, because this tells us how we can trigger Middleboxes, but every Middlebox might have its own policy. We also need to know not just the configuration, how the Middlebox, the weaknesses of it, but also how it's configured. Like what's its policy? So to study this, we went through Censored Planets data and tried to enumerate the 5 domains that are censored most broadly around the world. And we landed on these 5 domains, coincidentally spanning 5 different areas: pornography, gambling, social media, file sharing, and also sexual health. But the takeaway from this was that in general, Middleboxes differ in both their bugs and their configurations. And in general, attackers need to be savvy to both to make use of the attack. So these are surprising results, but in all fairness, Geneva made them kind of easy to find. And this leads us to the harder question of what's the impact of this? What's the potential damage one can do with this attack? And really what this comes down to, how we answer this question, is we would just be an attacker, attack ourselves, right? And then just start issuing requests to open servers around the world, right? And then we'll just see, once we've issued all these requests, where are the Middleboxes and how much data are they sending? But we don't know where all the Middleboxes are around the world. So the best thing we can do is send this traffic to every IP address. And in total for this paper, we actually scanned the entire IPv4 internet 35 times as a part of these results. So a lot of data. So this institution got a sizable number of packets from us. Yes. So let's see what amplification factors we can get from these types of attacks. Okay. And I'm going to show you a plot of the results here. And recall that we're not talking about weaknesses in TCP itself. We're talking about weaknesses in TCP implementations. And these weaknesses are going to be different for every Middlebox, configuration policy, etc. As a consequence, I can't just put a single number on the slide that says the amplification factor is X, because the amplification factor will be different for every IP address around the world. So instead, what I can show you is a graph of the amplification factors to get. So the y-axis is going to be the amplification factor, and the x-axis will be the IP address we got it from. And we've sorted these IP addresses by amplification. So all the way over here at the x-axis, this is the destination IP address that gave us the highest amplification factor, and then we'll go down from there. But please also note the log scales on both of these axes. Okay. The scales of these are to give away a little bit of the results. But I'm first going to show us a graph of how do these different packet sequences, how do these differ? How much do these matter? So this is what the graph looks like. We look at the amplifications from these different packets. You notice across the board, like these numbers on the left are startlingly high. Like I shouldn't ever be able to stand in front of you with an amplification slide that goes up to 10 to the 8. That's just a very big number. And I'll come back to that in a little bit, actually, because we call these guys at the front mega amplifiers, and their cause is kind of interesting. I'm going to circle back to these. But I'm also going to talk a minute just about this long tail down here. Because notice the amplification factor is pretty low, hovering right around 1 to 2x. But the sheer number of IP addresses we're talking about, 10 to the 7, 10 to the 8. The effect of these guys down here, that's nation state censorship. Actually, this long line right here, this is the Great Firewall of China. This is every IP address inside of China acts as a weak amplifier, because we can trigger the Great Firewall of China to every single one of those IP addresses. So in general, the packet sequence you choose, it does matter. All of them work a little bit, and some of them work in different cases. You can see some pretty big differences. And even all the way down here, this difference looks small because of the log scale. But this is the difference of hundreds of millions of IP addresses being amplifiers. But recall that what we're doing here, we're looking at different triggering domains, different policies, different bugs. How good can an attacker do that knew ahead of time the best thing it could send to every IP address? What could a perfectly well-informed attacker do? So this is the graph of what a perfectly well-informed attacker could do. It sent the optimal traffic to every IP address on the internet. And you can see the implication goes to crazy high numbers at this top. We can use this graph to see and answer some questions of how many IP addresses give us each amplification number. This is 300,000 IP addresses that give us greater than 100x amplification. We can also compare this to existing UDP-based attacks. So here's the number of that are equivalent to DNS, NTP, and then cache D. But overall, these TCP-based amplification attacks can be at least as powerful as their UDP-based counterparts. Now, I promised I would return to this big head of the graph up here, where you see these crazy 10 to the 8, 10 to the 9 numbers, right? But we call these mega amplifiers. And I want to spend a minute talking about what these are and how they work. Because as ridiculous as these numbers are on the left of this y-axis here, this is actually an underestimate. This is not when they stopped sending us traffic. This is when we stopped recording traffic. And actually, many of these IP addresses are actually offering infinite amplification. Let's see one example of how these works. In the paper we go through 2 mechanisms, and I'm going to show one of these right now. And when an attacker sends this traffic to its destination, what's really happening is that it's going between a series of routers. And what can happen sometimes is that there could be a routing loop. And in normal amplification attacks, a routing loop would basically end the attack right there. Right? The traffic didn't get to the server. But in cases where there's a middle box inside the routing loop, what's going to happen is that every time our attack traffic recircles the routing loop, it's going to re-trigger the censoring middle box. Okay, and every time it's just going to go around and around and around and re-trigger the middle box. What ends up happening here is for finite routing loops, this will give us an immediate amplification just by increasing our TTL. The higher the TTL, the longer the packet will circle, the higher the amplification. It's basically a free 240 to 250x amplification on top of the existing amplification. But where it gets more crazy is that we found some infinite routing loops that had middle boxes inside. And what's going on here is our attack traffic will circle forever or until some random packet drop occurred. And this was a huge problem for some of our early experiments because we go look at some data and we'd see traffic from scans we ran 3 weeks ago, and they would still be sending us data at their maximum capacity. Okay. And we found some of these in Russian censorship infrastructure, Chinese censorship infrastructure, and just other networks around the world. But this problem is broader than just censorship. Okay, and I actually went through the list of just some of our IP addresses and just picked out some notable amplifiers that I thought would be fun to look through. And you'll see that this is pretty widespread, and it's not just censorship, and it's not just offensive middle boxes. Even defensive middle boxes are problematic here, right? Holiday Inn and Suites in Salt Lake City, almost 100,000x amplification. Okay, the University of Ghent in Belgium, 312. The city of Jacksonville, Florida, that gave us a cool 240. Okay, so even defensive middle boxes can be dangerous and pose a threat to the internet. And because of this threat, we spent several months to disclose these results in a safe and ethical manner. And we worked with country emergency readiness teams, CERTs, around the world. We spoke to firewall manufacturers, DDoS protection services, basically giving them months ahead of time a warning of, hey, this attack is possible, please prepare yourselves. And I wish I could end my slides right here, but unfortunately, as of a week ago, I have an update for you on this, which is that these attacks are now happening in the wild. And as of, I think it's 1 week ago or 9 days ago today, the Akamai Security Intelligence Research Team published a report. They've started detecting these attacks in the wild against their customers. As of right now, the attacks are still on a more modest scale. They've seen around 11 gigabits per second, 1.5 megapackets per second. But attackers are still working to optimize this. And basically, this report is detailing that the attacks are getting increasingly powerful. So it'll be interesting to see over time how these attacks continue to evolve. And we're going to try and work with the Akamai team to measure these things. Yes.
So is that because of your paper or?
Oh yeah, they're directly, we saw some screenshots and they're directly using the triggers from our paper. Like down to some of those, like the domains we showed, like using exactly those domains, our packet sequences. Yeah. Yeah. Yes.
Sort of two questions.
Please.
So like the hotel in Salt Lake City.
Yeah.
So what is their motivation to repair this, which comes down to the attack in a while, right?
Yeah.
So eventually somebody's got to fix something.
Hopefully.
What is the consequence if they are acting as a reflector for everybody else? Like, do customers at the hotel perceive a difference? Does the person running the front desk go like,
Yeah.
wow, I can't stream YouTube today?
That's a good question. It kind of comes down to the exact circumstance of the deployment, and it probably is different in every single case. The motivation is probably their own quality networking, and also probably, I don't know, the US authorities probably won't take kindly to your machine attacking other machines. So maybe there's some legal motivation
Somebody
there.
come over. and make
Right,
it-
someone will knock on your door and be like, PS, please fix this. So not really sure.
Okay. And then the second one was, it was the plus.google.com, which is like on the social networking. So
Yes.
it doesn't even need to be a real, I mean, I
It's
just
just
checked. It plus is still there.
Yep.
But it just tells you that it's not there.
Yep, Google Plus is dead as a service, but it's
Right.
still censored around the world.
Okay, and so it's not whether the service is there, it's just whether it's on the
Strong
censor
blocklist.
list.
Yep, exactly correct.
So would it work equally well for Facebook or Twitter or something
It
else?
might, it depends entirely on how broadly that resource is blocked around the world.
Yeah.
So we chose that based on literally the trend numbers, and that was the 5 that came up.
Now we know why Google Plus didn't work.
Yeah, that's why. Okay, so this concludes my work on these automating approach to discovering these attacks. I want to finish in the last few moments because I'm getting close to the end of my time, and I want to be respectful of all your calendars. With just a brief discussion of some future work. Yeah. And in the current arms race of today, Geneva has given us a great advantage and really helped change the game for some of these circumstances. My future work is, some of my future work is to address tomorrow's censorship arms race. Because there are some things coming down the pipe that today's tools and systems are flatly not equipped to handle, Geneva included. So 3 quick examples of this. The idea of personalized censorship. Right now, it's the case that if you're in a network, really everyone in the network with you is affected by censorship in the same way. You can imagine a world very easily where the censorship you experience could be affected by your occupation or your social credit score, things like this. Right? So studying censorship and evading censorship in those circumstances is something much more difficult. More widespread or targeted use of throttling. We've already seen censors starting to do this. Measuring, we have throttling, right? Censorship is no longer a binary thing. And even just detecting censorship by throttling can be difficult. Right? Is it a network effect? Is it censorship? What's going on? And lastly, this idea of watching the invaders. And there's countries also starting to roll this out, where countries effectively spy on their users that they know are working on these cutting-edge censorship technologies, and just see what they work on, and then model where these techniques go and basically hunt the people out of it. So to address these things, we're going to need new techniques, new systems to address these. And for some of my future work, I want to work on this. I want to give one quick example of some future work I've been pursuing in this domain. And then I will promise to wrap up because I'm getting real close to the edge of the time. And this is this question of measuring censorship. And can we get a global view of censorship? Okay, because historically, most censorship, historically, most censorship measurements is studying the censors themselves. It was actually quite difficult to study the users that are being censored. How can we study the censored? And what we can do here is take advantage of idiosyncratic network behavior on behalf of the censor, and develop a system that monitors for the server-side network fingerprint of censorship. If you deploy the system, when the sensor operates, it ejects its traffic. Well, when this traffic reaches the destination, it can say, wait a minute, I've seen these packets before. This looks like the Great Firewall. Then you can work backwards in the connection to see what was the user doing that got them censored. This will let us answer questions like, what were these users doing that got them censored? What are users independently trying to access? How is user behavior affected by censorship itself? Now, deploying this just at Wikipedia is not very exciting because the only thing a user could be trying to access is Wikipedia, right? But more broadly, what we've been working on is deploying this at a large CDN. So I partnered with a large CDN. I'm unfortunately not able to mention it this time. but a large international CDN who's actually deployed the system, who developed and deployed the system, and we're able to detect real censorship events as they happen. We're still working on analyzing this data and sorting through this. We're really excited to start asking and answering these more difficult policy questions about how real users are affected by these things. Into the future, I want to deploy this everywhere. Campus networks, internet exchange points, hosting providers, more CDNs, etc. Now to wrap up, I can't close this talk without thanking the huge team of people that have worked on this. I've been advising undergraduate students on this project basically from the beginning. I've been leading a team of undergrads. And so throughout this, I've advised about 26 undergraduates to date. And these are the students that have published work with me. So huge thanks to all these students who have been on my team, and of course, University of Colorado collaborators on these projects. These students have also worked with me on some additional work, which I'm happy to talk about if people have questions on these. But I'm now like right at time, so I'm gonna stop right here. And thank you guys for listening. I'm happy to take questions.
Any question from the audience? I think we already have some enough questions, but yeah.
You talked about the mega amplifiers and you were saying that you're getting the data from the amplifiers that you had initiated 3 weeks ago.
Yep.
And then what did you all have to do after that? How did you stop that?
We tried to stop it. We tried to send packets. It wouldn't stop. So we basically just wrote some code to ignore it and then helped and made it so it wouldn't affect our existing scans. And then we just waited for their network to have random packet drop.
Is that amplification happening because of buggy implementation?
Could be buggy implementation. For that case, it was a routing loop. We could actually measure the routing loop, tracer out.
So the TCP is not checking the TTL field?
Yeah, so if you want to think of it like a bug, all the machines in the routing loop would not decrement the TTL. Yeah. And now there are some boxes that do that as a feature, right? For a machine to implement to operate transparently, they just don't decrement the TTL because then it's like they're not even there. So in some cases that's a feature, not a bug, but that's the root of the problem. Yeah.
Could you potentially use that as a way to overwhelm censor?
Yeah, it's another fun question. Abdul would love to talk to you all about that at some point later. So yes, we have been exploring that idea. It's a lot more difficult than it sounds because these networks are extraordinarily low provision, as you can imagine. I mean, these things are designed to handle like country level amounts of traffic. So as strong as our machine is, it's hard to compete with like China as terms of internet volume. But that being said, it's an awesome question and we've been working on it.
What was the question?
That was oh, sorry, I should be repeating questions. It was, can we use these types of attacks or can we flood sensors in general? Can we make them unavailable or flood or overwhelm sensors? Sorry, I'll try and get back in the habit of repeating questions as they come in. Any other questions? I think there's a few questions on chat as well.
We should do the chat.
Okay, sure. Okay, let's see. How does reward mechanism of rewarding for concise and explainability converted into code for a fitness function? That's a fun question. Basically, how do we implement a reward for conciseness? It's actually, I talk about it on the slide as a reward. Under the hood, it's actually a punishment. We just punish it for the size of the action tree. There's some other additional small punishments in there, like we punish it for the amount of overhead, the amount of traffic it's introducing into the network, things like that. Yeah, I hope that answers your question. Okay, would encrypted protocols slow down the process of the protocols as they'd have to be decrypted first before running? If Arvind is still in the chat, could you clarify what you mean by this? Are you asking if this would slow down the censor or if this would slow down Amoeba? Okay, but I might just move on to the next question. And if there's clarification that comes in, I'll answer that. With all this fuzzing of protocols, have you uncovered TCP/IP bugs that need to be fixed in existing non-censorship related stacks? Well, I mean, this slide says the answer is definitely yes. So yes, Geneva has found bugs in other non-censorship systems. I mean, we were first running this. It's found a bunch of bugs in Scapy. We found a bug with Docker for Mac. There's been a few like hiccups we've run along the way of just bugs we've encountered. But this is the highest profile non-censorship set of bugs we've discovered. I hope that answers the question, Neil. I think that's the chat. Any other
Okay,
questions?
I think.
How do you start this out of the initial thing? Is there
So we started seeded randomly. So the initial population pool is garbage. They almost all, like, they'll all fail when they start. But because of the fitness function, what will happen is the first generation will be pretty bad and pretty non-specific. And then subsequent generations will be specific to the network traffic, but it will still be killing the connection. And then it will be operating on strategies that keep the connection alive. And it's basically a fuzzer at that point. It does have the ability where you can seed it with an existing strategy. And we've done experiments like that in the past. But what we found is there's so many different, there's such a wide variety of strategy spaces in different places that in practice, it's often better to just start it clean and let it explore naturally. Yeah. Take it away.
Wow. Now, the end. Yeah, so I learned a lot. And then thanks to the speaker again.